Hello one more time. Today, my colleague Kinga Sałaciak, also from Jagiellonian University Medical College Krakow in Poland, and I will be discussing the application of advanced touchscreen technology in behavioral testing to assess cognitive function in rodent models. We focus on memory, learning, and also decision making. We will present you the advantages of this method in preclinical research and also its significance for advancing our understanding in the human nature, human health, neurobiology, and also drug discovery. So let's start with some background information. What is cognition? Cognition refers to a set of mental processes involving acquiring, processing, storing, as well using information. It encompasses a wide range of functions, including the attention, perception, learning and memory, language and communication, problem solving, decision making, and also executive function. So as you can imagine, cognition is very essential for everyday functioning, influencing how we perceive the world, how we interact with the world, and also how we respond to challenges and to opportunities. One of the most intriguing cognitive domains is executive function. Executive functions refer to the set of high-order cognitive processes that allow us plan, allow us focus, attention, remember some instruction, and also manage multiple tasks efficiently. So it's very essential for goal-directed behavior and also for adaptive functioning. Executive functions such as working memory, cognitive flexibility, attention control, emotional regulation, they kind of work together to support complex behavior, and they are vital for our performance at work, for our professional productivity, and also for the social interaction. Impairments in executive function, they can significantly affect our lifestyle, and they can be associated with various disease states such as ADHD, autism spectrum disorder, schizophrenia, traumatic brain injury, and also dementia. Currently, we are facing a growing prevalence of cognitive disorders. Over 55 million people are affected worldwide, and this number is expected to actually triple by 2050 due to the aging population. What is even more concerning is that existing therapies provide only minimal symptom relief, with no treatments available to stop or to reverse the disease progression. In addition to these medical challenges, the economic burden is also significant because the global cost is over $1 trillion in healthcare expenses. Therefore, there is increasing pressure and need to find novel compounds, to find novel drug candidates that would fully effectively treat the memory disorders. However, the process is far from simple, and drug discovery and development face numerous challenges. First of the challenge is that the memory disorders, they arise from very complex genetic, environmental, and also lifestyle factors. And it makes it difficult to really find specific therapeutic target. Secondly, many potential drug candidates, they fail. They fail due to the limited understanding of disease mechanism, due to the side effects, or difficulty crossing blood-brain barrier. Moreover, animal models, they often do not reflect human condition accurately. So that leads to unreliable preclinical results. And finally, clinical trials, they are costly, they are time consuming, and they have really high failure rates. But today, we would like to focus on one specific challenge, which is translational gap. But this challenge can be actually effectively addressed by using the touchscreen system method that we would like to present to you. So what is touchscreen system? It's an innovative platform that uses touch-sensitive screen for animal interaction. Animals, mainly rodents, they are making choices by interacting with visual cues, such as shape, on the screen. Additionally, this system allows for precise, automated recording of animal behaviors, reducing the human error. What makes the touchscreen system even more beneficial is the similarity to human memory tests, such as Cambridge Neurophysiological Test Automated Battery, and that allows direct comparison between animal and human data. Tasks like pair-associated learning or visual discrimination, they assess memory and cognitive flexibility, mirroring the human tests. Importantly, the touchscreen system is not just one behavioral test. It's a huge platform offering a wide range of paradigms, as you can see here in the graph. I mentioned to you already about 2 tests, but researchers, they are continuously developing the new tests. You can design your own custom task, or you can choose one from 14 pre-validated options. What makes this system even more powerful and interesting is flexibility, because each task can be modified or combined to assess multiple cognitive domains at once. Also, the difficulty of the task can be tailored to match your specific research goal and also cognitive abilities of the animal models. So all these features of touchscreen system actually open up endless possibilities for studying behavior and cognition in innovative way. By selecting the appropriate task, specific cognitive domains such as cognitive flexibility, working memory, decision making, spatial learning, they can be explored. And this versatility makes touchscreen system a very useful tool for advancing the understanding of brain function, but also to develop treatments for cognitive disorders such as Alzheimer's disease or some other neurodegenerative condition. Today, however, we would like to focus only on one single task, which is 2 choice pair weights visual discrimination task with reversal learning. This task allows to assess key cognitive domains, 2 key cognitive domains. First one is visual discrimination, which actually refers to the ability to recognize and also to distinguish between various visual stimuli, such as shapes, colors, and patterns. And the second one, cognitive flexibility, it's a skill to adapt or to switch different tasks, rules, strategies when the situation changes or when we get some new information. So 2 choice pair weights visual discrimination task with reversal learning, it's a common test used in neuroscience and also in psychology. It helps to check if animal can distinguish between 2 different images and to see how well the animal adapts when the rule is changing. It also tests basic associative learning that doesn't strictly rely on hippocampus. These cognitive functions are often impaired in disorders as schizophrenia, Parkinson's disease, Huntington disease. So that's why this paradigm is very beneficial for investigating the pathomechanisms that underlie those disorders, but also it helps to identify the potential new drug candidates. Let's move on to protocol. Kinga, the floor is yours.
Okay, So before I will be explaining the steps of the procedures, we need to get over a few basic ideas will be actually useful later to understand how the pairwise discrimination task looks like. So first we have a trial, which is actually some kind of a single round of experiments where we have the image, which is presented on that screen, and we record the subject's reaction to it. On the other hand, we have a session which is actually some kind of scheduled period during which the animal performs some kind of a series of trials. Yeah, so sessions can have a fixed number of trials or last a certain amount of time to measure performance consistently. Moreover, each day actually only one session can be performed. Yeah, that's why actually the touchscreen task may last some pretty long, like several weeks. So what do we need to perform these tests? So we need to have a specialized equipment, which is called touchscreen operant chambers. Yeah, they can come from various suppliers. So for example, here you have a presented from the Camden Instruments, but you can also buy it from the Med Associates, but you can also have some custom-made version. Yeah, so the design actually varies on the species. Yeah, so we have some smaller version for the mice and some bigger version for the rats. Yeah, also this design may depends on experimental needs, but we have some basic features that are similar. So here, for example, this is actually the operant chamber, and here you can see the operant chamber. So above it, we have cameras. Yeah, that are later, let's say, connected to the monitor and to recording device. Yeah, let's just say it's not obligatory, but I would say it's pretty useful to see what's happening inside the chambers. Of course, the whole system is controlled by the specialized software, which is typically provided by the chamber supplier. What's also important and noted that actually these chambers are placed in the sound and light attenuated boxes. So here you have these blue cabinets. They have their own ventilation, and their own ventilation system. So they reduce some kind of external noise and stress, ensuring that we'll have some controlled environment, and therefore we'll get some more accurate data. So here you can see actually the top view of the operant chambers, which consists of the several key components. So first of all, we have a touch screens, that they are very high sensitivity to the touch by the nose or the paws. In front of the touch screens, we have some black plastics mask, which has some kind of response windows. How these masks are actually built depends on the task. So for example, in this two-choice visual discrimination task, the mask has two response windows. So the purpose of using this kind of the mask is to reduce some kind of the accidental touches and makes actually respond areas clear. Yeah, opposite to the touchscreen, we have the magazine. So we have it here and here. Yeah, so this is the place where the reward is delivered, because actually touchscreen paradigms are food motivated tasks. So which means that when the animals perform correctly a trial, they will get the reward. The chamber is surrounded by the trapezoidal walls that actually focus the animal's attention on the touch screen and the reward area. Additionally, what you can see here, we have the infrared beams on the both sides of the walls and also inside the magazine. So we can track the animal's movements and the entries. Okay, so what else do we need for the experiment? So of course, we need to have a subject. So we can use either mice or rats, of course, depending on our experiments, our research question, and available equipment. So since we are working with the animals, we also need to have a proper housing and some standard rodent food pellets. We also need some kind of the cleaning materials, so like 70% ethanol solution, some kind of a cloth on the paper to clean the chambers between the animals to reduce the odor that could affect their behavior. But most importantly, we need a food reward. So like I mentioned, in touchscreen task, we use appetitive stimuli. So animals are rewarded with sugar pellets or strawberry milkshake for completing the task correctly. Sugar pellets actually works well for rats, while in case of the mice, we can use either liquid or dissolved food. And actually, liquid rewards can be even more flexible, and especially in a situation when we have some motor changes or some kind of other factors that may affect chewing or motivation. So if we have all necessary reagents, we can proceed with the test. However, before I move on with the protocol description, I'd like to cover some kind of the general consideration, especially for those of you who are not familiar with working with animals. So first of all experiments involving live animals must be approved by relevant institutional and governmental bodies, and of course follow their regulation. So, but to ensure the reliable results, we need to have some kind of standardized routine. So this means that the training, weighing the animals, and feeding them needs to be done at the same time each day. It is also important to use the same operand box for each animal and have the same experimenter or team for consistency. Additionally, balancing the use of different chambers and testing across different experimental groups help us ensure the fair and valid results. So now we can move for the protocol. So first phase is about the preparation for the pre-training. So as I mentioned twice, the touchscreen are food motivated tasks. So animals get the reward if they perform correctly. However, as this task can last several weeks, over time, animal may lose motivation. So to prevent it and to ensure some kind of consistent task performance, we implement mild food restriction before training and throughout testing. So how does this body mass control look like? So first of all, what we need to do is to calculate the free feeding weight. So we weigh the animals for 3 consecutive days while they have a free access to food and water. And from that, we can calculate their average free feeding weight. Next, we can start the food restriction. Yeah, so we gradually reduce the animal's weight over the course of some 3 to 7 days until they reach the target weight, which is typically 85 to 90% of their free feeding weight. So to achieve that, we actually carefully control the daily intake of the food by the animals. So they give the rats approximately 4 grams per 100 grams of the body weight. In case of the mice, we give them 1 gram per 10 grams. So imagine that if we have the mouse that weighs 25 grams, we give them around 2.5 grams of the food. In case of 300 grams rat, we give them 12 grams of the food. So once the animals are close to this target weight, we can, let us say, move forward to the next phase. But still, we need to maintain the food restriction throughout the touchscreen testing. What's important, of course, we need to regularly monitor the weight. We need to avoid the situation that the reduction of the weight will exceed 5% per day. That can be really dangerous for animals' health, especially in case of the mice. And of course, we need to be sure that their weight will stay above 85% of their free feeding weight. So in case of the mice, we weigh them every day. In case of the rats, we can do it twice a week, but I would say it's better to do it every day. In the situation that we are performing the experiments with some juvenile animals, we need to take into consideration that they need to still continue to grow. So we need to adjust the target weight weekly to support some kind of proper and normal development. So to do that, actually, we are using some available growth curve specific to the species and the strains. So for studies here, I'm showing you some kind of the growth curve for Worcester rats and for bulb C mice. So this kind of the growth curve actually guide us in making some kind of the necessary adjustment to their target weights. So this actually ensures that the animals continue to grow and develop normally while maintaining the appropriate level of the food restriction. The next step and the preparation for the pre-training is the introduction to the reward. So we're getting the animals used to the food pellets and the milkshake. So we just simply put sugar pellets. Yeah, it can be scattered on the floor of the milkshakes in some kind of the place in some kind of shallow dish for 1 to 3 days. 3 days are actually better. So the purpose of this step is actually help the animals to get familiar with the rewards they will later receive during the task. So once the animals reach the target weight and realize that the sugar pellets and milkshakes are not only edible but actually tasty, we can begin the next phase of this paradigm, which is called pre-training. Yeah, so pre-training is all about teaching the animals to touch the screen in some kind of slow, step-by-step way. So this phase actually can have 3 to 5 stages depending on how complex the task is. So for the two-choice visual discrimination task with virtual learning, the pre-training consists of 5 steps. So we have a habituation, initial touch, must initiate, and the punish incorrect. And each step is really important to get the animals ready for the main task. So let's begin. So first step is about habituation. So it involves simply placing the animals inside the chamber to allow it to become familiar with the environment and learn where it can find the reward, which will be later essential for, say, the proper test. So you can see here, I hope, that the animal, let's say, is exploring the chamber. Yeah, so now it's actually currently eating from the magazine. Yeah, so it gets, let's say, accustomed to the whole system. Yeah, so of course, let's say it can be a little bit stressful in the beginning for the animals. Yeah, it's really try to escape. Yeah, but it's still, let's say, it's find its food magazine. Yeah, so it tries to eat some kind of the food. Yeah. So what's the purpose of this step? So it's just simply to get the animals comfortable with the environment, yeah, and the touch screen before moving on to the more complex steps. So this session actually helps to reduce the animals' stress and anxiety by showing them that this environment, this chamber is actually safe. So what the animals need to do to be advanced to the next phase of the pre-trainings, it just simply needs to eat all rewards given during the session. So it's a very easy step, nothing too challenging. What's actually, it's worth noting that in the case of this phase, we have some differences between the species. So in case of the mice, actually habituation consists of the 2 stages. So we have a 10-minute session first with the reward, and on the next day, we have a 20-minute session with the milkshake delivery. In the case of the rats, actually habituation consists only on 1 stage with a 30-minute session with the sugar pellets delivery. So why is that? Why do we see such differences between the species? Usually mice are more anxious and stressed, and especially the strain that we are using, bulb C. So because of this, they need to have these 2 phases for habituation to help them to adjust more gradually for the task. The next phase of the pre-training is called initial touch. So in this phase, actually, there'll be no reward waiting in the magazine. So here the mouse needs to go through a series of the trials where the image will be displayed in one of the response windows. So here the image is displayed in the left windows, animal selected, and gets reward. It is signalized by the light in the magazine. In case of the initial touch, animals actually receive the triple reward, yeah? So it's really a big, food gain for them. Between the trials, so the situation where the animals select the image and gets reward, we have this trial interval. So that in case of the mice, it lasts 5 seconds. So imagine the situation, because actually it's not demonstrated in this video, that if the mouse doesn't touch the image within the 30 seconds, the image actually disappears, but the mouse still will get some reward, but smaller, still signalized, of course, by the magazine light. So the reward is actually only 1/3 of the normal amount given for the correct touches. And actually, it will be better visible here in the video in the rats. So here you can see that the image is displayed, but the rat is actually not very interested in, say, in coming nearby to the touch screen, yeah, for that. So after this 30 seconds will pass, we have the light in the magazine, and only one sugar pellet here is given to the animal, yeah? So it's take the reward, the lights goes off, yeah? And we have this intertrial interval. In case of the rats, we set up for the 10 seconds. And now we can see the next random image appears on the touch screen, and now the rat is approaching it. Yeah, so it selects, and now you can see the triple rewards comes to the food magazine. So we have a free sugar pellets for the rat. So what's the goal of this phase, of this initial touch? Yeah, so we try to teach the animals to touch the touch screen on purpose. So simple these shapes, let's say like squares, circles, they appear randomly on the screen, and to encourage them to explore. So when the animals touch the image, it gets the reward, yeah, triple this time. So what animals need to do to get advanced to the next phase? In case of the mice, it needs to complete 100 trials within this 30 minutes. In case of the rats, it needs to complete 60 trials within 60 minutes. But like I mentioned, as during the one day, we can perform only one session. So this stage, not only this stage, but all can last even several days. So now the next third phase, yes, we have a habituation, initial touch, then we have a must touch. So in this phase, actually animals, as the name suggests, must touch the image on the screen to get the reward. So actually this stage will help to refine the animal's ability to interact with the screen by introducing the simple rule. Only the touches on the image will trigger a reward, while touching other areas or doing nothing won't result in any reward. So actually this phase, let's say it's a bit different from the previous one, where the animals still receive some reward, yeah? So see here, you'll see, yeah, the images, yeah, so here the image is displayed on this right side. Mouse is not, let's say, a little bit interested, but now it touches and it gets this single reward in the magazine, yeah? So like mentioned, it's signalized by this light. The next phase begins, yeah, and the animal gets the reward. And similar in rats, yes. So you will see here. So when the image will appear, yeah, on the screen, yeah. So animal now needs to touch this kind of the stimuli to get the reward, yeah. So it touches, yeah, and it gets only the single pellet, yeah. So we have a smaller reward compared to the previous stage. So what is the goal of these steps? So actually, we try to more enhance the animal's interaction with the screen by just implementing this rule that reward is only given the situation when the image is touched. So we strengthen the animal's ability to focus on the task, preparing, of course, it for more complex task later on. So what do animals need to do to get to the next stage of the pre-training? So in case of the mice, they need to complete 100 trials within just 30 minutes. In case of the rats, they need to complete 100 trials within 1 hour. Okay, so we have 3 phases behind us, and now the next one, the fourth. So it is called must initiate. So this stage is actually pretty similar to the must touch phase, but now the animal has to start the trial by triggering the image representation. So the trial starts when there's light, there will be light in the magazine. Yeah, and animals need to put its head here. Then we have an image display, and when animals touch the image, it gets reward. In case of the mice, it's very quick response. So here you can see the animals need to start. Yeah, the image is displayed, animals choose it, and gets the reward for that. So in case of the rats, the same similar procedure. So to start the presentation of the simile on the touch screen, rats needs to put its head here, the image is displayed, rat selected, and get the single sugar pellet for that. So what's the purpose of these steps of the training? So we try to teach the animals to start each trial on its own. So animals needs to use notebook into the magazine to make the image appears on the screen, helping to understand that it has to engage with the task before anything happens. So this phase actually helps the animals to take more control and prepare it, of course, for the more advanced tasks that will require starting the trials and some kind of the good timing. In case of the must initiate, actually both species have the same criteria. So they need to complete 100 trials within 60 minutes. So 4 stages behind us, the fifth, the last one. So it is called punish incorrect. So in this stage, we introduce some kind of punishment if the animal will touches the blank screen instead of the image. So similar, the trial starts when there will be light in the magazine. So animals need to start the trial. Yeah, and the image is displayed, but the animals choose the blank screen. So actually you can see it is punished with this some kind of timeout period when we have this whole chamber elimination and with no reward. So the next phase, the next trial, animals now touches the image, so and it gets the reward, yeah, for that. And the same in the case of the rats, yeah. So first, rats needs to, let us say, put its head into the magazine to start the trial. Yeah, it needs to select this image. However, it chooses the blank screen. So it is punished with this light chamber elimination and no reward. Yeah. Now we wait just 10 seconds, this inter-trial interval. Yeah. And the next trial needs to start by putting its head. And now the rat select the image and gets the reward. So what's the purpose of this stage? So we try to teach the animals that the touching the wrong area of the screen leads to some kind of negative consequences and delay. So this phase adds punishment to discourage the animals for making incorrect choices and helps improving task accuracy to get them ready actually for the test phase. And here actually we have a little bit more advanced criteria. So animals not only needs to complete, let's say 100 trials within the 60 minutes, but it needs to do this with some kind of certain level of correct responses. So in the case of the rats, we require for them for 80% of the correct responses. In the case of the mice, only 70%. these differences, they are related to the situation that usually rats has better focus and learning abilities than mice. So therefore, rats requires just only 80% accuracy, while mice that are usually more anxious and less focused have some kind of a lower threshold to account for these differences. So actually, we finished the training. So now we have this actual test phase, yeah? So which is called pairwise discrimination. So during this phase, animals learn to discriminate between the two stimuli, between the two images presented on the screen. So one stimuli is correct, and in our scenario is the marble, which actually leads to get reward. And we have the second option, the fun, which is incorrect, offering no reward. And similar situation. So the trial needs to start, yeah, when the mouse put its head into the magazine. Okay, so we need to wait. Animals, okay, great. And the image are displayed. Now the animals choose correct image, yes, so it gets the reward. Now we have this inter-trial interval, the next trial, yes, so animals needs to start it, so putting its head here. Okay, and now it will choose the wrong, the fan, so it gets punished, yeah, by this whole chamber illumination for that. Okay, and now we have the next phase, which is called next scenario. So we have a pairwise discrimination in case of the rats. So here actually we are using a little bit different images, like a plane and a spider, that actually research shows that they works better for the rats. So the plane here is the rewarded option, and the spider is in punished one, is the incorrect one. So as usual, trial needs to be started by the animal itself by putting its head into the magazine. Image are displayed. Now the rats choose the correct one, the plane, so it gets the reward, the sugar pellet. In the scenario that the animals choose a wrong option, you see here the images are already displayed. Rat hesitates to choose something, but next it actually select the spider, so it gets the punished by this intense light and no reward for that. So here in this test, in this pairwise discrimination, like I mentioned, animals must choose between the two stimuli. So touching the correct stimuli will result in a reward, while touching the incorrect one will lead to the timeout with no reward and also some kind of punishment by this intense light. So the goal of this phase is to train the animals to distinguish between these two images and make the accurate choices, which is actually some kind of the key for assessing this cognitive function, like learning, memory, and decision making. There are some, let's say, variation with the same stats, such as reversal learning, that I will tell you in a minute about, where we have where the correct and incorrect stimuli are swapped to test the cognitive flexibility. However, even during this stage, we can use some pharmacological manipulations to study the drug's effect on the cognitions, like in case of that, some visual memory, or we can use some kind of, I don't know, genetic models, yeah, to assess their cognitive performance and so on. But like I mentioned, today I would focus about this little bit upgrade, so reversal learning. So animals needs to also pass some criteria to be moved on to this reversal learning. So we require the same for the mice and rats in this scenario. So they need to complete 100 trials within the 60 minutes with 80% accuracy for that. So reversal learning is actually the same as pairwise discrimination, with this one difference, that now they're marbles that was previously, let's say, rewarded and now will be punished, and choosing the fun will lead to getting the milkshake. Yeah. So we have the trial starts. Yeah, so actually animals needs to put its head here. And the image are displayed. So for first situation, the animals choose wrongly, so the previously rewarded option. So it gets this timeout period, this intense light, and no reward. Yeah. Now we have this ITI. The next trial starts. Animals needs to put its head here, and the images are displayed. And now the animals choose the new version, the better option, so the fun. So it is rewarded with the milkshakes. And the same actually works for the rats. Yes, so rats needs to start the trial, yeah, by putting this head here. The image will be displayed. But first, let's just say rats decided to choose the previously rewarded option, the plain, yeah? So it gets punished by doing it, yeah? And in the next situation, yeah, as time flies by, yeah, the animals will start the trial. Yeah, so we have a spider plane, but now let's say it chooses the spider, so we'll get the food palette. So in reversal learning, actually rodents needs to forget the old reward choice and learn the new one after the stimuli are switched. So we test their ability to adapt and adjust to some kind of the changes. Yeah, of course, during the first days of reversal learning, animals will keep choosing the old rewarded option out of habit. But over time, the animal must stop this old behavior and start selecting the new rewarded option to get a food. So this task, like we mentioned, is actually assessing this executive function, which is called cognitive flexibility. So this ability to adjust behavior in response to some kind of changing environmental contingencies. So as mentioned before, these impairments in reversal learning are actually associated with various neurological and psychiatric disorders. That's actually what makes this task valuable for the research. You may ask, actually, how can we decide when to stop let's say performing these experiments? So actually it's a little bit flexible and depends on us. We can actually wait until all animals will meet the criteria, like completing 100 trials within 1 hour with 80% accuracy, or we can have a scenario when we only need to have that the control group will fulfill the criteria. Or imagine the situation that we can also have some kind of set fixed time for how long the reversal phase should last. So this choice, like I mentioned, depends on us, on our experimental design, some kind of hypotheses, and how the experiment is actually progressing. Yeah? So imagine this whole experiment, yeah, the lasting several weeks. So during this period, actually, we collect a large amount of the data that actually can help us to understand the animal cognitive processes. So we can analyze the several parameters. So we have some more important, let us say, less. Yeah. So I would start, let's say, with some kind of the basic one, which is accuracy of their responses. So we measure the percentage of the correct choices. We can do it, of course, during the Paws discrimination and the reversal phase. So actually, it assesses the learning and adaptability of the animals. The next parameter we can measure is actually trials and sessions to criterion. So this is the number of the trials or sessions and needed to reach some kind of set accuracy level, which will show some kind of learning speed of the animals. So fewer trials, fewer sessions will mean the faster learning. We also can measure the errors that animal will commit during these experiments. So more errors will suggest some more difficulties in learning and adapting. And actually, we can also distinguish some very specific type of error, which is called perseverative errors. It's a situation when the animals will keep choosing the old rewarded option continuously. So imagine this scenario that animals performing the trial is choosing the wrong image, yeah, the next trial starts, but the animal still continues to choose the wrong image, and the next trial, another mistakes. Yeah, so these continuously made error are called perseverative errors. So actually, they give us the information about this cognitive flexibility and inflexibility. Three more parameters we could analyze. So first here is in correction trials. Correction trial is the type of the trial in which animals actually given some kind of the second chance to correct incorrect result. So once again, imagine this situation. We have a trial, animal choose the wrong image. So now actually it is moved on from some kind of normal trials to correction trial. In case of the correction trial, the layout of the images is the same. So the images will be displayed at the same positions. Yeah. So if they are to, let's say, move on from these correction trials, animals need to choose the, say, rewarded option. Yeah. So if they choose it, it will be moved back to some kind of the normal trials. But if it will continue choosing this wrong image, and actually it will stay and performing these correction trials over and over. So the number of the correction trials during the experiments can tell us how well the animals can learn from the mistakes they made during the trials. The next parameters, which is a little bit different, is called reaction time. So we measure the time taken from the presentation of the stimuli to the animal's response. So it makes this actually measure this decision making as speed. And so the longer motivation. The next option, so the next parameter is a reward collection, so latency to reward collection. So this measures how quickly the animals actually collect the reward after making a correct choice. So it provides us the information about the motivation and also about the motor function. So actually, there are a little bit more parameters we could actually analyze based on the experiments. However, these are some kind of basics, or say the most interesting one that can give us a really big information considering the animal's learning, motivation, and decision-making processes. So actually, from my side, that will be all. So I presented to you, let's say, the protocol step by step, and also some kind of results. So now let's discuss the benefits and drawbacks on the touchscreens.
So let's start with the benefits. For sure, the touchscreen system can mirror the human cognitive tests, so it makes it very useful to compare animal and human data, and this is critical for the drug development. Additionally, the touchscreen system, it detects very subtle cognitive impairments in learning, in memory, and it provides very detailed data. Additionally, the touchscreen system is automated and standardized, so it allows to reduce the human error, it allows to speed up the research, and also to test multiple animals at once. It's also ethical and efficient because it's less stressful for animals, and also it reduces the number of animals that is needed for study. And as I mentioned at the beginning, it can be customized to assess various cognitive functions, and that's why it's very useful for the drug discovery. Additionally, it can be integrated with more advanced techniques like optogenetics, like photometry, video tracking, and also electrophysiological recordings. So that would allow researchers to gain more deep insights by combining the behavioral data with the precise neural activity measurements. Moving forward to limitations. What are the main limitations? So definitely the touchscreen system itself and its price. You need it to perform the experiment, you need it, and it's costly, and also it requires expertise to operate. Kinga mentioned that the training is required for animals. This is another limitation because training animal to interact with this touchscreen system sometimes can be really time consuming, especially in case you have the animals that are not really motivated. Another limitation would be that the task may not cover all cognitive domains, all aspects of cognition, for example, social behavior. And another limitation would be that some species or some strains, they may struggle to engage with touchscreen. So that will limit the usage of this system. To wrap up our presentation, we might ask, could video games for rodents be the secret weapon in finding new treatment for human brain disorders? Sounds crazy, but it just might be. And I promise you that it will be the last slide to sum up and to highlight big benefits of touchscreen system. For sure, please remember that it's very translational. So it allows to mirror human cognitive assessment. It allows to evaluate the cognitive impairments that are seen in the neuropsychiatric disorders. It's automated and very precise. It allows also, I think we didn't mention about this, it allows also to detect very small cognitive changes early. So that would be crucial to test the drugs that are aimed into mild cognitive impairments, like those that can be seen at the beginning, early stages of Alzheimer's disease. It can also support the long-term tracking of cognitive changes. And this is very essential for studying chronic effects of some drug candidates. We also mentioned that it's not invasive, it's optimized, it's less stressful for animals, it provides very reliable data, and importantly, it aligns with 3R rules because it allows us to reduce the number of animals. So in summary, the touchscreen system, it's a very powerful tool in the drug discovery and development, offering the flexibility, offering the precision, and strong relevance to human cognitive function. Together with Kinga, we would like to thank you, our entire team, especially to the head of our team, Professor Karolina Pytka, but also to our PhD students, Angelika, Ola, Paulina, Ania. Additionally, we would like to thank you to the Dean of our faculty, Professor Marcin Kołaczkowski, Dr. Joanna Śniecikowska, and Dr. Adrian Newman-Transedi, who provided us with the compound that we were testing.